today's lecture, I shall first be discussing how can we prepare dialkyl derivatives or dialkyl carboxylic acids from ethyl acetoacetate. So what I am trying to tell you is that we will be discussing the synthesis of dialkyl acetic acids. So as I said, that when we have to prepare a monoalkyl derivative, we bring about the alkylation of sodium ethyl acetoacetate is done with alkyl halide when we get a monoalkyl derivative. Now this monoalkyl derivative is treated with sodium ethyl oxide when we will get a sodium salt of alkyl acetoacetate. And now this sodium salt of alkyl acetoacetate will undergo alkylation with alkyl halide, and this alkyl halide may be same as the one which we have used previously, or it may be different, resulting in the formation of dialkyl acetoacetate. And when we carry out the acid hydrolysis of this dialkyl acetoacetate, we will get a dialkyl acetic acid. So let us see these reactions as to how are we carrying out this reaction. So as you can see on your screens, that is the molecule of ethyl acetoacetate is treated with sodium ethyl oxide, and in doing so we are getting a sodium salt. And as I said in my earlier lecture, the bond between this sodium metal, sodium and methylene carbon is an ionic bond which is represented by a positive charge on sodium and a negative charge on methylene carbon. Now this methylene carbon, this sodium salt will react with a molecule of alkyl halide, resulting in the formation of alkyl derivative of ethyl acetoacetate. Mind you, here this derivative is monoalkyl. Whereas what do we want to prepare? We want to prepare a dialkyl acetic acid. So we will now again repeat the first step, that is the reaction of this monoalkyl ethyl acetate with sodium ethyl oxide, and then we will get we will then treat that with alkyl halide when we will get a dialkyl derivative of ethyl acetoacetate. Now this will be made to undergo acidic hydrolysis. And when we carry out the acidic hydrolysis, as I have told you in my previous lecture, that what are we going to do here? We are going to break the bond between the carbonyl carbons. So and the methylene group, now what we are taking here is dialkyl methylene group, and we are going to break the bond again between the carbonyl carbon and the ethoxy group. So when we do this, what you find that the carbonyl carbons are electron deficient. So the OH will go on to them and we will get a molecule of acetic acid. And then H will go to the methylene carbon, resulting in the formation of CHRR. And this on hydrolysis, now you have to remember when we are doing the hydrolysis, OH is going to the carbonyl carbon, that is you are going to break the bond between the carbonyl carbon of the ester group and the ethoxy group. When you do so, you will get dialkyl acetic acid and you will get a molecule of ethanol. So in summary, what you have to remember in this reaction, that is first you will convert ethyl acetoacetate into its dialkyl derivative. And after you've done that, you will bring about the acid hydrolysis. This is very important. During acid hydrolysis, what you have to remember is you will break the bond between the acetocarbon and the methylene carbon, and then you will break the bond again with the carbonyl carbon and the ethoxy group. And you will add OH to both the carbonyl groups. So when you do so, from one side, from left side, you will get an acetic acid. From the middle part, you will get the dialkyl acetic acid, and of course we will get a molecule of ethanol as a side product. Now let us go on to synthesis of dicarboxylic acids. So when we are carrying out the synthesis of dicarboxylic acids, we can prepare succinic acid, we can prepare adipic acid. So when we are doing the preparations, let us first start with the preparation of succinic acid. So when we are talking of succinic acid, what you have to remember is how many carbons does succinic acid have in it? It has 4 carbons in it. Whereas if I talk of glutaric acid has 5 carbons in it. And when we talk of adipic acid, it has 6 carbons in it. So what I mean by saying that when we are talking of succinic acid, we are talking of 1,4-butane dioic acid. When we are talking of glutaric acid, we are talking of 1,5-pentane dioic acid. And when we are talking of adipic acid, we are talking of 1,6-hexane dioic acid. So these are the IUPAC names. But when you will be asked to do a particular conversion, you will be asked by this common name in your exams. So for example, the first question that I would like to discuss with you, and which is important from examination point of view, is convert ethyl acetoacetate into succinic acid. So when we are carrying out ethyl acetoacetate into succinic acid, what you have to remember is that the first reaction will be the same. That is, you will treat ethyl acetoacetate with sodium ethoxide when you will get sodium ethyl acetoacetate, which you can see on your screens. Here ethyl acetoacetate has been treated with sodium ethoxide when we are getting a sodium salt. Now what are we going to do? We want 4 carbons in our dicarboxylic acid. Whereas, please remember, from ethyl acetoacetate, we are just going to get 2 carbons, which is the methylene carbon and the carbonyl group, carbon from the carbonyl group of the ester group, ester moiety. So these are the only 2 carbons which we are going to get. So how many carbons do we need in succinic acid? We need 4 carbons. And along with that, we need 2 carboxylic groups. So how do we bring about this reaction? So now what we are going to do is, we are going to take the sodium salt of ethyl acetoacetate and treat it with chloroacetate. So when we treat it with chloroacetate, what happens is, as you can see on your screens, the methylene group, that is the negative charge on the ester anion, acts as a nucleophile and it makes the bond with the CH2COO-C2H5 group, that is chloroacetate group. So what happens here is that the sodium being electropositive, it has a positive charge, it picks up a chlorine, that is Cl- from chloroacetate. Why does it do so? Because chloro group is more electronegative as compared to the carbon, and it pulls the electron towards itself, so it has a negative charge on it. So when it has a negative charge on it, Na will pick up a Cl from there, getting NaCl. As a result, now this CH2 will have a positive charge on it, and the ester anion will act as a nucleophile, making a bond between CH2COO-C2H5. So what do you find here? That a new bond is being formed between the methylene carbon of the ethyl acetoacetate and the CH2 group of the ethyl acetate. So we get a new bond is being formed here. Now we had 2 carbons, that is from the methylene carbon and the carbon of the ester group. Now we have to bring about the acidic hydrolysis of this intermediate that we got here. And if you remember, when we were preparing an alkyl derivative of acetic acid, in that case we were using 2 molecules of water. But in this case, we want to prepare a dicarboxylic acid. So we will have to use 3 molecules of water to bring about hydrolysis here. So as I have told you earlier on also, you will break the bond between the carbonyl carbon and the methylene carbon. And from there to the carbonyl carbon you will add OH when we will get a molecule of acetic acid. H will go to CH and it will be converted into CH2. And then again what we find that when we do the hydrolysis of the ester group, OH will go to the carbonyl group, converting it into COOH group, and H will go to the ethoxy group, converting that ethoxy group into the ethanol molecule. So what do we find now? As you can see on your screens again, what do you find here? That is, you're getting a molecule of acetic acid here, and a bond will cleave from here, which will result in the formation of succinic acid. That is CH, H will come from water here. This will be converted into CH2, and you have CH2, CH2, COOH and COOH, which is your succinic acid. This is how we are preparing succinic acid. So let me quickly again summarize this reaction. That is, we will treat ethyl acetoacetate with sodium ethyl oxide when we will get a sodium salt, and this sodium salt on reaction with chloroacetate will give us an intermediate, which on acid hydrolysis will give us a molecule of succinic acid. And here we will be using 3 molecules of water to bring about the hydrolysis. And you have to always remember that the bond between the carbonyl carbon and the methylene group will be cleaved. The bond between the carbonyl carbon of the ester and the ethoxy group will be cleaved, and we will get the succinic acid from the middle part of the molecule. From the left hand side we will be getting acetic acid, and from the left hand side we will be getting ethanol, which are the side products of the reaction. Now let us go on to synthesis of higher dicarboxylic. So when we talk of synthesis of higher dicarboxylic acids like glutaric acid, as I've said, that glutaric acid is pentane 1,5-dioic acid, adipic acid, which is 1,6-hexane dioic acid, or pimelic acid, which is 1,7, that is heptane 1,7-dioic acid. These are prepared when 2 moles of sodium salt of ethyl acetoacetate are treated with dihaloalkanes. And what you have to keep in mind is what will be the position of the 2 halogen atoms. So when I am saying dihaloalkane, you know that this clearly means that the alkane molecule has been substituted in such a way so that it has 2 halogen atoms attached to it. Now we know that it can be a gem dihalide. Gem dihalide is CH2Cl2 or CH2I2, in which both of the halogen atoms are attached to the same carbon. Then we can have a vicinal dihalide. Vicinal dihalide is when the 2 halogen atoms are attached to the adjacent carbon atoms. For example, we can have 1,2-dichloroethane or 1,2-dihaloalkane, right? Then we can have an isolated dihalide, that is, we can have 1,3-dihalide, that is propane 1,3-dihalide. So these are the different types of dihalides which we can use here, right? And now when we are talking of these and the nature of this dihalide will decide whether we are getting glutaric acid, we are getting adipic acid, or we are getting pimelic acid. The thing which is common in all these preparations is that we shall be using 2 moles of sodium salt of ethyl acetoacetate, and it will be the nature of dihaloalkane which will decide what will be the nature of what will be the dicarboxylic acid that will be formed. As you can see on your screens, two molecules of sodium salt of ethyl acetoacetate are being treated with a dihaloalkane. And this I had clarified just 2 minutes back, that the nature of the dihaloalkane will give us the type of dicarboxylic acid that we need. So the CH2, when I am putting that CH2 into N, that is N is the number of CH2 groups. If this N is 1, that means it is a gem dihalide. If it is N is 2, that means it is a Wisnel dihalide that we are using. And if say N is 3, then we say it is an isolated dihalide that we are going to use. So now when we are using this dihaloalkane here, so the number of the carbon atoms will decide what kind of carboxylic acid we are getting. Here I am showing you a general reaction. So when a reaction takes place between two molecules of sodium salt of ethyl acetoacetate and 1 mole of dihaloalkane, we will get an intermediate. And now this intermediate on acid hydrolysis, that is reaction with concentrated KOH in presence of dilute HCl, will give us 2 molecules of acetic acid as side product and 2 molecules of ethanol as products, because we are using 2 molecules of its sodium salt of ethyl acetoacetate as our substrate. And we will get a alkane dioic acid, and the nature of the alkane dioic acid will depend upon the value of CH2 group, methylene group, put in the bracket. If N is 1, what will we get? We will get glutaric acid. If N is 2, you will get adipic acid. If N is 3, you will get heptane dioic acid or pimelic acid. So now let us look into the mechanism of the acid, the reaction. So this is what again you can see on your screens, that when N is 1, it is glutaric acid, that is pentane dioic acid. When the value of N is 2, it is adipic acid, that is hexane dioic acid. And when N is 3, it is pimelic acid, that is it is heptane dioic acid. So the general mechanism of the reaction is that in this case we will be taking 2 molecules of sodium salt of ethyl acetoacetate, and we will be treating it with say gem dihalide or any dihalide. So what happens in first step is that the sodium salt of ethyl acetoacetate acts as a nucleophile through negative charge on methylene carbon, and it makes the bond with the carbon of the methyl dihalide. So when we are talking of the alkyl dihalide here, so now you know that iodine is more electronegative as compared to carbon, so it will pull the electrons towards itself, as a result of which now this carbon will have a positive charge. And what do we find here? That Na plus abstracts I minus, and we get NaI as the side product, and a bond is formed between the methylene carbon and the carbon of the dihaloalkane. So what we get here is we get a intermediate, which you can see on your screens. Now this intermediate now reacts with the second mole of the sodium salt of ethyl acetoacetate, and the same reaction which I had explained earlier again takes place. That is, the negative charge on the methylene group of the ethyl acetoacetate acts as a nucleophile, makes the bond with the substrate, that with the intermediate which we've got, resulting in the formation of again another intermediate, which you can see on your screens. Now this intermediate, now what has happened here? Look at the structures carefully. A bond is being formed between this CH, this CH2 and this CH. So this CH2 which is making a bond here is coming from our dihaloalkane. So if this is 1, N is 1, so this will be CH2, and we will basically get, if you remember, we will get here glutaric acid or pentane dioic acid. So this is what I wanted to make clear here, and this is a very important point. You can simply write it down also if you do not want to do the mechanism of the reaction. What you can do is, you can write here as CHNA, CH positive Na, CH negative, Na positive, CH negative, Na positive. And then you can write your dihaloalkane in between. Na, subtract NaI from here, subtract NaI from here. That is, subtract 2 moles of NaI and make a bond between this methylene carbon CH2, which is coming from the dihaloalkane, and the methylene carbon here. So this is what is the intermediate you will get. And now when we carry out the acid hydrolysis here, you have to remember we will be using 4 molecules of water here. Reason being, what will you do? OH will come here. You remember, you have to break a bond from here. You have to break a bond from here. That is, you have to break a bond between the carbonyl carbon of the aceto group and the CH group, and again between the CH group and the carbonyl carbon of the ester group. So when you are doing so, what are you getting? Let me start from left to right. So what will be doing? CH3COOH, which is separated out. You will get a CH2 on the top, and you will get a CH2 at the bottom side of the part of the molecule also, because we are using 2 molecules of ethyl acetoacetate. Now in the third, and again we will be using 2 molecules at the lower end also, and then again a bond will be similarly broken from this side. So what we find, that the 2 aceto parts, the aceto groups of ethyl acetoacetate, are converted into 2 moles of acetic acid, and from ester we are getting 2 moles of ethanol, and that group is being again converted into COOH group and COOH group. So this group, that is the ethyl acetate COETOOC, is being converted into a carboxylic group by hydrolysis. And what you have to remember here is that OH will go to the carbonyl group and H will go to the ethoxy group, resulting in the formation of a dicarboxylic acid. So when you have to prepare this, now you do not have to do the mechanism. So what you can simply do is, that is, you write down the 2 molecules of ethyl acetoacetate, one in front of the other, and in between them you write down the dihaloalkane, whichever you are taking, depending on the type of dicarboxylic acid that they are asking us to make. And then you make a bond between the methylene carbon of the 1 ethyl acetoacetate, the CH2N group from the dihaloalkane, and again the methylene carbon of the second molecule of ethyl acetoacetate. This will be your intermediate. Now when you have to break the bond, what you do? You separate the aceto parts of both the intermediates, that is both the parts of the ethyl acetoacetate moieties in the intermediates, convert it into acetic acid, add H to the methylene group, again add H to the second part of the methylene group, and then break a bond between the carbonyl group of the ester and the ethoxy group. Again break the bond at the lower half between the carbonyl group and the ethoxy group. This will give us a dicarboxylic acid from the center part of the molecule, which can be your glutaric acid or adipic acid or pymalic acid, depending on what type of dihaloalkane you have taken. Now I would like to discuss synthesis of alpha beta unsaturated acids. So when we talk of preparation of beta unsaturated acids, this is using Norwegian condensation reaction. This is a condensation reaction of an aldehyde or ketone with an active methylene compound in presence of a weak base. For example, we can carry out the reaction, say, of acetaldehyde with, when we are talking of reactive methylene compound, we can take malonic ester or we can take ethyl acetoacetate. And when this reaction takes place, we get a conjugation in the molecule, and because of this conjugation, we are getting a unsaturated carboxylic acid. Now, why is the product unsaturated? Or it is because due to the loss of water molecule after a reactive methylene compound adds on to the carbonyl group of the aldehyde or a ketone. And in this case, we like to use weaker bases. We do not like to use strong bases, because if we carry out the reaction in presence of a strong base, then an aldehyde or a ketone may undergo self-aldol condensation. So the yield of the reaction will be less. So supposing now, if you look into the general mechanism of this reaction, what we find that a ketone reacts with a reactive methylene compound in presence of a weak base, like we can take a amine here. And during the course of reaction, what we find that the oxygen of the carbonyl group, this is the simple way of doing the reaction, and the two hydrogens of the methylene group, which are acidic in nature because of the presence of two electron withdrawing groups, which are Z1 and Z2, are eliminated off as water. As a result of which, what we get here is a unsaturation in the molecule. We get a double bond between the carbonyl carbon and the methylene carbon, resulting in the unsaturated compound. Now, what you have to remember here is, now when we are talking of an activated methylene compound, it can be ethyl acetoacetate. And I will be discussing the preparation of crotonic acid by reaction of ethyl acetoacetate with acetaldehyde. So what is observed, that when we treat ethyl acetoacetate with acetaldehyde in presence of pyridine or diethylamine, which is a weak base, it will give us an alkylidene derivative of ethyl acetoacetate. And this ethyl alkaline derivative on acid hydrolysis will give us an unsaturated acid. So as you can see on your screens, it's a very simple reaction. We've written a molecule of ethyl acetoacetate and we are carrying out the reaction with acetaldehyde. So what happens in the course of this reaction? Oxygen from here, H2 from here, not the carbon, H2 and O are eliminated off as water, resulting in the presence of alkylidene derivative of ethyl acetoacetate. You know what is alkylidene? Alkylidene is when the two functional groups are attached to the same carbon and the molecule has a double bond in it. So we are now carrying out the hydrolysis. And now you know, when you carry out the hydrolysis, you will carry out the hydrolysis with the help of two water molecules. And when we do that, OH will come here, H will come here, and then what will happen? OH will come here and H will come here. So from this part, that is from the aceto part, will be converted into acetic acid, and when we put our H on the methylene carbon, we will get CH double bond CH, CH3, and then we are bringing about the hydrolysis of the ester group, and when we do so, OH will again go to the carbonyl carbon and H will go to the ethoxy group, resulting in the formation of crotonic acid. And you know, crotonic acid is alpha beta unsaturated acid. Again, I have shown the reaction on your screens, and you can clearly see that during acid hydrolysis, the bond is being cleaved between the carbonyl carbon and the methylene carbon, and again the carbonyl carbon and the ethoxy group, resulting in formation of crotonic acid. Now in my next lecture, I shall be discussing the preparation, the mechanism of this reaction and preparation of ketones. For this, I had consulted the books by Bell and Bell and Morrison and Boyd. Thank you.